Woohoo! We are recording, and this is 9.3, part 1 for Math 75. And what are we going to be talking about in here? We're going to be talking about rates of change and the derivative. This is very exciting. And so to begin with, we're going to go back to average rate of change. Now, this is something that you study a lot in Math 60 or Algebra 2. And it is something that we've reviewed a little tiny bit in this class. Basically, what we're looking at is the slope. So we've got the slope. M is the slope, which is the rise over the run. Y2 minus Y1 over X2 minus X1. And then I've got this expression, which is really, this is the average rate of change. So what does it represent? Well, if we look here, I've got Y2 minus Y1. That's f of b minus f of a over x2 minus x1. Well, what is x? Well, here x is b, and here x is a. And so basically, this is just a fancy way of talking about a slope. But then we're going to go a little bit further. We're going to say, can we find the slope of a curve? And our first answer is no. No, of course not. Slopes are not for curves. Slopes are for lines. So here we have, and I realize that in the video you guys are seeing through the pages and it's making it hard. So let me move my other papers out of the way. Hopefully it's a little easier to see what's going on there. And we will see that if this is our function, the black curve is our function. Now, the very first most important part of this is that f is continuous. So there can't be any breaks, any jumps, any of the goofy stuff that we were talking about in the last section. F has to be a continuous function. If I pick the point A here and a point B there, and I look out the slope, right? The slope of that we're going to say is f of b minus f of a over b minus a. That's going to be the slope of this pink line. It's not, in fact, the slope of this curve because, again, the slope measures how steep or how shallow a line is or a line segment. So it's the line segment here that's in pink. That's the slope we're looking at. So we're like, well, okay, this comes pretty close though. I mean, the curve itself is mostly increasing. Maybe it tops out here. It's hard to tell whether it starts to decrease or not. And the pink line segment is going up. It's approximately correct. But, you know, overall, it's just an average. It's just an estimate. So this line segment would not be especially helpful. And then, and this is where the magic happens, and then we get a couple people in the late 1500s who are like, but what if we were to make these points closer together? What if we were to slide B closer to A? So f of B starts to slide down the curve. What would happen then? And what we're going to say is, well, we get the average rate of change over a smaller interval, right? This is a big interval, at least it seems to be in the way I've drawn it. If we move B closer, it'll be a smaller interval. And then we say, okay, so what happens if we slide A and B to the same point? And at which point you should say, wait a minute, you should not whistle like that because it's painful. And I'll say, yes, I know. But then also we would say if A equals B, then B minus A is 0. And this is a problem. Why is this a problem? Well, because the denominator here is B minus A. So we can't have 0 in the denominator. So this is, oh no. So, and I say, well, that's just silly because if A equals B, then B minus A equals 0. So the denominator is 0 and the whole thing falls apart. If only we had a way to get really close to 0 without actually using 0 itself. And then we say, woohoo, limits to the rescue. Because a limit is an attempt to get really close to something without actually being there, right? You get really, really close. So it turns out everything we've been doing in the first 2 sections, not totally a waste of time. Instantaneous rate of change. So let's go ahead and look at what I've written. So I've written what we had before, f of b minus f of a all over b minus a, but I'm sticking something else in, and that is this. I'm saying, let's slide b really close to a, which is what I say right there. Let's get b and a real close together. Okay, so we call the resulting limit the instantaneous rate of change of the function. What would this look like on the graph? Well, so b would slide closer and closer to a, and that would mean that f of b would slide closer and closer to f of a. And so, for example, if b were there, f of b would be there, and our little line segment would be there. And if we move a little bit closer, like here, my new f of b would be there, and then my line segment would be right there. And we start to notice something. If I move the point here, keep going. Oops, sorry, I forgot my x value here. This corresponds to this point. So if we're at this point, if b's moved all the way to here, then f of b is right there. And so my new line segment that I'm drawing, wow, that's getting really, really close, right? And so we just keep getting closer and closer and closer until finally we have, let's see if I can draw it. This is going to take a ruler. It's not the easiest thing in the world. It's an estimate. But I get a line that looks a little bit like this. So this is as close as I can get to the tangent line. I know there's this little gnat guy who's really excited about calculus. This is very exciting. I know, it's very exciting. He's just like dancing, having the best time. So if we look here, here's f of a, there's f of a, and if we draw this line right there at A, that is the tangent line, and the slope of this tangent line is the instantaneous rate of change. It's the slope of the graph at that point, which is kind of a weird concept. What does that even mean? Well, I tried to write it out here. So you know when I write a whole paragraph, I'm trying to get at something that's a very elusive concept. But I'm going to do my best. Let's talk about it. In plain English, or as plain as I can get it, it's the direction you are headed if you are following the function right up to the point A and then keep going in that same direction. So if you see this, you see the graph, it's going like this, it's going like this. At A, we stop, and then we just go off in a straight line. So it's the point you would keep going if you get to A, and then you stop curving with the curve, you go straight out in a straight line. One way to think about this is to consider a baseball. For our purposes, assume it has no spin, or else the whole thing goes kind of wonky. You might swing your arm in an arc to build up speed. So let's do an overhand throw. So here you are. Oh, well, I don't know why the smile is on the side of your face, but I'm just going to draw this. And here's your hand. You've got a very long arm. That's a baseball hat. I'm sure you can all tell with the bill and everything. There you are. So there you are. Your hand is right here, and there's a baseball. It's very large. We've decided to do a very exciting large baseball. And what's going to happen is as your arm moves, it stays connected. I don't know how you're doing your hand behind your head, but you're doing it. So you're gonna throw the baseball, but then as soon as you let go, the baseball, if you let go right there, the baseball, even if you swing your hand all the way, right point, when you let go. So if you are swinging your arm around, and I'm not sure if this drawing follows the laws of physics or not, if you're holding the baseball, here's the baseball, and you let go right there, it will head off in that direction. It will not keep turning with your hand. Whenever you let go of the ball, it goes. So if you're throwing something, you can't make it keep bending. It'll head off in a straight line, according to physics. Now, is this entirely true with baseballs? No, you can put spin on them and do all sorts of shenanigans to get them to move in slightly different ways. But generally speaking, when an object gets tossed, as soon as you stopped pushing it, it heads in a straight line. This is the tangent line as well. So again, following the curve, we stop at this point and we head off in a straight line. That's what the tangent line is. Okay, I know you're all like, oh, great, it's the tangent line. Just what I always wanted. I've been asking every birthday for a tangent line. And finally I got one. I'm so excited. And it gets better. So we're going to go into the formal definition of the derivative. As it turns out, the previous limit is not the most convenient form for the instantaneous rate of change. Instead of considering a and b, we look at x and h, where x takes the place of a and h is the distance from a to b. So h equals b minus a. So I want to do a comparison. This is the picture we just drew. Our new picture is going to have, we're going to start here. That's x. This distance here is h. So this is x plus h. This point is the point x, f of x, right? Because that corresponds to a, and f of a. And this point up here, now this is, because this is x, and this is, we've gone h to the right. Let me scooch this up just a little bit so you can see that. So this is x plus h, f of x plus h. Now, hopefully this is starting to remind you of something we did a couple chapters back with that I called the difference quotient, because we're about to write it right here. So f of b is now f of x plus h. F of a is now f of x. And down here, we've got x plus h for b minus x. And that is f of x plus h minus f of x all over x plus h minus x, h. And this is the difference quotient that we already started talking about a few chapters ago. And then we got distracted by money, you know, as happens. That is the tale as old as time. Okay. So let's take a look here, compare and contrast. This is the format we use when we were not being specific. We just had 2 points, A and B. Now we're going to transition to a slightly different set of variables, but these still could represent any situation. I'm just going to call my first spot, my first location on the x-axis, x instead of A. And my second spot, instead of calling it B, I'm going to label it x plus h. And this is the distance between them, is h. Then the function values are f of x and f of x plus h. So I am still just taking the slope of this red line segment. So I'm going to put, I know, arrows everywhere. So this is the slope of the red line segment, just like this is the slope of this red line segment. Okay. Now, as I get the next page, what I do want to say is, in this class, we are given really very little time to talk about this. If we were going to talk about this in a class where we were just going to focus on calculus, we would have more time to talk about it. We would talk about all the deeper meanings. Right now, for this class, we mostly just say, oh, isn't this nice? And then what we're going to quickly do, so in 9.3, we're going to spend a little time with the theory, but we're going to very quickly transition into how do we use this. So this is, bear with me, we got one more big page of theory and then we're going to start doing stuff. So the limit that we started with the B's and the A's becomes this limit. So let's take a look. Don't look at that yet because that's complicated. F of B, f of x plus h. F of A, f of x. Remember the B minus A, the distance, is h. Now here we were saying B needs to get closer to A, but in our new situation, what needs to happen? If we want to move these points closer together, the distance, the h, has to get very small. So that's what we're going to do. We're going to let h get really, really small. Tiny, infinitesimal, which is a fun word to say. And when we do that, when we set this up with this wording, with the difference quotient, we end up with f prime of x. So this is f prime of x. But a lot of people don't say f prime. They just look at this and they say, oh, the derivative of f. It's called the derivative. And this whole thing is called the definition of the derivative. And remember, what is it we're doing? We're finding the tangent. And in fact, here we're finding the slope of the tangent line. Okay. So for those of you who haven't fallen asleep or gouged your eyes out or just started spontaneously crying, all of which are very reasonable responses if you've never seen calculus before, because this is just so weird. This is not what you think of as math, and I agree, it gets really weird. But it's really great and useful. Why is that? Well, if you are looking at the stock market, and let's say you're watching the stock market, and the stock market ended here today, and you wanted to guess where is it going to go in the future. I mean, you could make a lot of guesses, but if I'm looking at the stock market and I'm watching the news and I think, well, and there's nothing really big going on in the news. You know, there hasn't been any big shocks economically or politically. So we just expect the stock market would just kind of keep muddling along as it did. What you could do is you could say, you know what, I would love to know which direction it was headed, because these seem pretty smooth. So if I look at which direction let's see, kind of try to guess which direction it was already going. I could make a guess that the stock market would head in that direction, right? I would take the tangent line. So what we would want to do to try to guess where the stock market was going would be to look at the direction it was already headed in and kind of guess it goes out that way. Now, is this going to be a good guess? Well, it might be. I mean, there are a lot of things that could happen. It could head down suddenly because bad news comes in the middle of the night. It could head up suddenly because good news happens in the middle of the night. More likely, it's going to just keep going, the way it does, and maybe there is bad news. We can't know this. But for a little short distance, little tiny distance there, just long enough to make some guesses and put in some, invest some money overnight and hopefully make some money in the morning, you might be able to guess where things are going. Now, as you get further out, as you get further away from the point where you calculate the tangent line, you're going to be really wildly off. Generally speaking, the tangent line is only good in a small space. Okay, so that is, from an economics perspective, we're looking at the derivative in terms of looking at, or the tangent line, which we're also looking at the derivative, in terms of what's going to happen, so we can anticipate. We can also make some guesses on choices about revenue and cost, and we're going to get into those applications in a couple chapters. Woohoo! Okay, let's come back to f of x and f prime of x. So we've got f prime of x, and you say it's called the derivative of f. Now, there are a couple of other ways to write the derivative. And I know you're going to say, wait, why are there other ways to write it? What's wrong? Was it like there were two people who were fighting to get published first, and one was British, and so he got his book published, and one was German and didn't have the contacts and couldn't get the attention, and so they've got two different systems that have been fighting ever since? You would be absolutely correct. There is the Newtonian version, and there is the, I don't know how to make it an adjective, but Leibniz was the name of the other person. And of course, there were other people working this stuff out too at the time. So it's a lot of excitement, but because there were a couple of different groups of people working on this, there were different ways to write it. So one way to write it, f prime of x. Another way to write it is dy dx. Now, this looks weird, but it actually has this beautiful meaning, but we don't have time to go into it a lot. But I'll just remind you that there is the understanding that you've got y on top and x on the bottom, because basically what we're talking about is slopes. No matter how fancy this gets, this is all about slopes. This one is generally pronounced dy dx, or the derivative of y with respect to x. It's a slightly different system. You're going to see these two interchange, and I know it feels like a lot right now, but once I start showing you how to do what you're going to do, it's going to make more sense, I hope. Fingers crossed. Okay, so what in the world would we want the derivative for? Well, for us, the derivative gives us the slope of the tangent line, which is going to help us predict what's happening in the future. The instantaneous rate of change of the function. This is going to give us information that will help us make decisions. If you're in a business situation, should you produce more? Should you produce fewer? How are your costs changing? How are your profits changing? The marginal cost. There we go. This is an approximation of the cost to produce one additional unit. So we can figure out, is it going to cost? What is it going to cost to make one more? The marginal revenue. If we make one more, how much extra revenue can we get? The marginal profit. If we make and sell one more, how much money can we make? And interestingly, it will also tell you the maximum and minimum points of a function. So if you already know the function that dictates your revenue function, for example, or your cost function, if you know what that function looks like, you can calculate what the maximum and minimum points are, so that you can actually make decisions, like if you want to maximize revenue or if you want to maximize profits. And believe it or not, it's a little weird, but sometimes you don't want to maximize profits. Sometimes you don't want to maximize revenues. There are lots of things that could happen. So these are all just ingredients that go into this big pot that I'm losing my metaphor, that creates the stew that is the decision matrix for your company. How's that? There we go. Okay, so I'm going to stop here. The next video is going to have all of the much more practical applications. I'm actually going to show you. We are going to calculate a derivative. You will see it. You will love it. We'll have so much fun. It'll be amazing. Much better than cats. I hope you guys have a great day. Remember to get some vitamin D, get some exercise, get lots of sleep, stay hydrated, and math on.